Okay, good morning, everyone. Thanks a lot for the nice introduction, Bjorn, and thanks for the organizer for giving me the opportunity to present the work I've done during my PhD. So as Bjorn said, I'm now a postdoctoral researcher at Utrecht University. I'm doing some protein complexes modeling using docking approaches, but what I'm going to introduce you to do and present you to do is the work I've done during my PhD. And it was about the semantics for integrative and immersive visualization on analysis of molecular data. So let's start first by introduce you a bit the field of application. Here, structural biology, the molecular data that I've evoked in a title. Structural biology is mainly about studying the protein function through the deciphering of their 3D structure and dynamic, following the famous axiom that says that the protein function is mainly or significantly impacted by its 3D structure. Why studying proteins? Because you might all know they are really important in the cell. They are responsible for most of the metabolism path on what makes the cell basically work in your body and in organisms. So are responsible for many functions, as I say, cell mobility, cell structure, DNA conditioning, etc., where 3D structure play quite an important role. Since we were studying, since in structural biology, we're studying 3D structure of proteins, we of course wanted quite early to visualize them. So it started with some basic way to study proteins, and then of course with the evolution of the technology, evolution of what we could use to visualize 3D structures, we arrived with some recently with some technology of immersive environments where basically you can explore and walk into your molecule, into your proteins, into your system. And that basically the application we wanted there in our work. It's to how we could improve or maybe develop how an expert could explore its protein in 3D. And it started with an observation. So what is the usual research pipeline in structural biology? You can split it in 3 main steps. Of course, it's quite broad, but you can split it in 3 main steps. Experimentation, you try to get some experimental data that's gonna give you some insight about the 3D structure of your system. So NMR, cryo-EM, X-ray crystallography, that are some of the techniques that allows you to get some insight into the 3D structure of your complexes. Then using this data, you can create a model of your structure with your computer. And finally, I told you, so a static protein brings some information, but doesn't bring the whole information. You might need to understand how it works. So you want to simulate it using molecular dynamics, docking, etc. You put this structure into motion. All along the research pipeline I just explained, you have the visualization and the analysis. That's two important fields that the structural biologist is gonna explore. Until now, for most of the research pipeline you have in structural biology, these two domains are kind of split, they are separated. So each time you get some data, you go first to visualize them, for instance. Then you go, you get the data you have, you analyze them, you look at what you get. Then when you reach the next step, you visualize them again when you did your 3D modeling, and etc. So you go always back and forth between the visualization and the analysis. Okay, nowadays we have tools that kind of simplify this thing, even if it's still kind of split. But when you are in immersion, when you are in a 3D immersive environment, it's kind of get complicated to go from your visualization to your analysis, because you basically kind of restrain to your 3D environment. So it's not that easy to manipulate both data at the same time, both visualization data, and analysis data. So our goal was to see if we could merge these two fields by using some by basically linking them on using some representation of the data that will allow us to just merge all the data together for an expert, for a structural biologist expert. So that's going to my first part, where how would you link such visualization on analysis? Of course, it's not something new. Visual analytics is a field that basically takes care of that, or try to address this challenge by merging scientific representation on information visualization. Here we're talking about analytical data. So this is kind of a famous field, and of course it had some application in structural biology already. So DIVE, KineMage, Next Generation, Cytoscape are some software, for instance, that try to address this challenge and mix these two ways to represent data. What they have in common that they are based on an homogeneous formalization of the data you're going to observe, and that you're going to try to link. Okay. So basically, what the approach they tend to follow, it's to create some ad hoc links between the data. So you have an individual you are interested in here in your visualization space. Let's say this residue there, and you have this hydrophobicity scale value that is associated. But from the moment you want to add some analysis in your workflow in your platform, and it has not been thought previously, you get to the point where, okay, this link doesn't exist, so you need to create it. Which is okay, you can create it, but of course it makes things, whenever you want to add some new analysis, some new types of data, it makes the pipeline quite complicated to set up. Same thing, some individual can be linked on many data, so for each of this kind of value, you need to create some new links. So our motivation there were either a way to extend the data types on information by automatically linking them to the data you're already manipulating. So you have new sets of data, new set of information types you want to add. Could you have something generic enough, a platform generic enough to naturally add them without too much trouble? And then when you want to access information that are linked to this to the data you're manipulating, can I naturally access them without set up these HADDOCK links one by one to access this information? That's more about the dynamicity of the platform. So our idea was, okay, let's try maybe to have a semantic representation of the knowledge. So having a high-level representation of your knowledge to be able to basically define all the concepts you're going to manipulate and then easily link them and manipulate them. So what is the semantic representation of the knowledge? That's a bit the core of our research. It was so it's basically the semantic and syntactic definition of all the concepts you're going to manipulate in a particular field, here structural biology. And that has some specification, of course. So we want to define all the concepts by their properties. So simple example of phenylalanine has an hydrophobicity scale of 2.8. Okay, that's something. So I define the phenylalanine concept with a value associated, a property associated. I have a hierarchical classification of concept. What does it mean? You try to classify your concepts by already creating a first link between each other. So an amino acid is a molecule which is a biological component which is ultimately an object. You can set up relationship between the concept. So a molecule is composed of atoms. And it's quite important, and that's something that was quite important for us, you can reason to extend the representation, meaning that once you created these links there, these two links, you can easily get to the conclusion that an amino acid is also composed of an atom. And you didn't have to create this particular links. It comes automatically from your semantic representation of the knowledge. So now you get, in the platform we imagine, you get this knowledge representation in the middle. So each time you want to access values or properties of an individual, you create this knowledge base, and then you get access to a value. So meaning that if you have another value, you just add it in your knowledge base, and then you access it directly. Okay, that's quite a simple example of what you can do with this knowledge base. Of course, so there is many ways to represent, to have a semantic representation of knowledge, and we needed to choose a formalism to represent all these concepts. We identified some constraints, 3 main constraints for our platform. We needed a hierarchical data representation via concepts and properties. I already explained you how it was working. Some advanced reasoning possibility in order to extend the ontology or the data set whenever you have new information, or even creating new information from the existing information you already defined in your ontology. And finally, and that's more about the immersive part, you wanted to have an effective query time to stay within interactive time. You don't want a user, when you perform an action, to wait few seconds or a few minutes to get an answer. You want something that can be used in real time. So we explored some different formalism, and one formalism that kind of stand out to do so, it's the semantic web. So it's part of the family of the description logic. Sorry, it has been created by Tim Berners-Lee within the W3C. So it groups what we have in the two first constraints, description and reasoning. And it has also some libraries and implementation possibilities that make it quite useful in interaction time. So semantic web can be split in three main layers. The knowledge base, which groups basically the definition of your field, so ontology plus domain facts, sorry. The facts themselves, so what you get from your experiments. And finally, the query language that will allow you to access those data. So if we look at the knowledge base, I already told you it's basically the definition of your field of application, your structural biology. So you try to basically have a network of concept and relationship that will define all the data you're going to manipulate. Of course, one of the main part is the biomolecular knowledge. That's all you know about structural biology. But we wanted here to mix basically values that are quite heterogeneous. So you need also to define in your ontology what are 3D representation, 2D representation, 3D interaction that the user might have with his data on 2D interactions. So it's not only about the knowledge of your domain, but it's also about the knowledge of what kind of interactions, what kind of representation a user might want to deal with this data. So that's the knowledge base. Then the facts base. Fact base is basically, as I told you, you use some experimental value to instance your ontology. So based on the concept, on the properties you've defined in your ontology, in your knowledge base, you're going to create some individuals basically that are going to define your study case. And finally, the query interface allowing you to interrogate, but also modify the database at any time. And it's quite important. We said that we wanted something generic and dynamic, so you want to be able to extend easily this database depending on the analysis you're going to perform, on the action that the user is doing at a time t. So if we come back to the schema I've made before, how does it work? So you have the knowledge base, in red there, which is the definition of your different concept. Then you have the facts base, so taking from your experiment on your case studies, and you have the query that basically each time you perform an action, each time you perform a selection, let's say, this database is queried and then give you back an answer. So now that we have this semantic representation of the knowledge, what can we do with that? And it's quite interesting because we can extend this representation to go even further. In immersive analytics and in immersion in general, it's sometimes complicated to do some complex tasks. Selection of subparts of a graph, of a cloud of points, perform analysis on a particular part of your system, change the representation, this kind of complex task in desktop setup, they are performed through clickable menus, some command line instruction. The problem is in immersion, of course, in 3D immersive environments, you don't have access to such a thing, or you have access, but it's a bit more complicated to do so. So we need a better way to perform these complex tasks when we deal with heterogeneous data, analysis on visualization again, but in parallel. So we've created an interpretation engine that basically transforms keywords into specific action, selection, filtering, representation, for the visualization and analysis spaces in order to basically synchronize any action of the user to be performed on both spaces at the same time. So it's based on the ontology we developed to define the field. You don't need to know any software-specific syntax, so that's kind of an advantage, meaning that you can basically use this full database and plug anything you want to it. It should be agnostic of the software you're using. And you have a possible disorder of given keyword. That was an extra feature that we basically discovered kind of when developing the interpretation engine. You can get rid of a specific order. So you have a new interface now between the user and the application. And you have some natural interactions that are possible, that are device-free. Quite interesting in immersive environments, of course, because you can make use, for instance, of vocal recognition. So how this interpretation engine has been developed? So it's split into 3 main steps. First, keyword recognition. So we use a simple keyword spotting algorithm that basically recognizes keywords from a vocal command. Okay, it tries to match any keywords to the ontology we have and give us back the answer. Then, once the keywords have been recognized and are part of the ontology, we try to classify them. And we have 5 main categories that we define to make up the command: action, component, identifier, property, and representation. The Sparkle queries I'm talking about, that's basically the query system we have in a semantic web. And finally, once you have your keyword, they are classified into your categories, you can create your final command. So you merge concept and individual, identified in the previous steps, into an application command. And we've derived a main frame for this command, a main form, which is you want to perform an action, you get a parameter associated to this action, which is not mandatory. You can get just the action. If it's a selection, you might just get the action without a parameter, and then you apply it to a group together with an identifier or not. And so thanks to that, just by emitting some keyword, vocal command with some keywords, you get access to a full command that you can apply to your spaces. So just a quick illustration of what you can do then with that. So we developed a proof of concept where we mixed a viewer, here PyMol, which is kind of well-known in structural biology and broadly used, with a web page where some analytical graph can be created. So these 2 spaces, visualization spaces on your left and analytical space on your right, are basically both linked to the database I was evoking on some handling management. So what you get there in the analytical space, you have the possibility, so you query your database and you get all the values that are basically, that you can plot or graph into 2D representation. So the user chooses what he wants to observe. And once he decided to plot, here we plot the distance, but so we use a molecular dynamic study where you have a protein system that have been simulated, and you get for each time frame of this trajectory, each snapshot, a distance compared to the reference structure that is there. So the expert selected 3 first models with a vocal command, and then these 3 models are displayed synchronously in your visualization space, right? So you get that just with a selection command. Then second step, okay, you want to change a bit the scale. You are interested in a specific residue in your amino acid in your model. So it is selected in the same way. You just emit a vocal command, and you want to select particular residue in this model. So you do so, and synchronously you have them displayed in your analytical space with some associated values that you might want to plot, and you basically propose to the user to plot. So that's one of the many possibilities you have with this platform. You can go even further. You have, as you see, you have different scale of study. So you basically each time synchronously act within your visualization space on your analytical space by querying your database. So our objective, just a reminder, was to fusion visualization and analysis spaces in a unique and immersive working space. So we did that in several steps. The step I just explained before. We create an extensible knowledge database thanks to the Semantic Web. We set up an automatic transformation process of scientific data you get from experiments to the knowledge base, and you synchronously you fusion your visualization visualization, on analysis space, thanks to direct interaction. And finally, and that's the future work we want to do, you have this possibility to use multiple modalities, in input and in output. Thanks to this knowledge base on the database associated, you can set up some collaborative tasks where command can be emitted by 2 users, for instance. So that's a multimodality in input. And in output, you can, since you have informed interaction, So since you have informed interaction, you can propose some relevant analysis depending on the task of the user is performing in his space. And it was my last slide. So thanks a lot for all the collaborators that work on this study, and thanks to you for your attention.